A quantum Turing machine, also a universal quantum computer, is an abstract machine used to model the effect of a quantum computer. It provides a very simple model which captures all of the power of quantum computation. Any quantum algorithm can be expressed formally as a particular quantum Turing machine. Such Turing machines were first proposed in a 1985 paper written by Oxford University physicist David Deutsch, suggesting quantum gates could function in a similar fashion to traditional digital computing binary logic gates. Quantum Turing machines are not always used for analyzing quantum computation. The quantum circuit is a more common model. These models are computationally equivalent. Quantum Turing machines can be related to classical and probabilistic Turing machines in a framework based on transition matrices. Shown by Lance Fortnow, Irayama, Oya, and Volovich have developed a model of a linear quantum Turing machine. This is a generalization of a classical QTM that has mixed states and that allows irreversible transition functions. These allow the representation of quantum measurements without classical outcomes. A quantum Turing machine with post-selection was defined by Scott Aaronson, who showed that the class of polynomial time on such a machine is equal to the classical complexity class PP. Informal sketch. An easy way of understanding the quantum Turing machine is that it generalizes the classical Turing machine in the same way that the quantum finite automaton generalizes the deterministic finite automaton. In essence, the internal states of a classical trademark are replaced by pure mixed states in a Hilbert space. The transition function is replaced by a collection of unitary matrices that map the Hilbert space to itself. That is, a classical Turing machine is described by a 7-tuple. For a 3-tape quantum Turing machine, the set of states is replaced by a Hilbert space. The tape alphabet symbols are likewise replaced by a Hilbert space. The blank symbol corresponds to the zero vector. The input and output symbols are usually taken as a discrete set, as in the classical system. Thus, neither the input nor output to a quantum machine need be a quantum system itself. The transition function is a generalization of a transition monoid, and is understood to be a collection of unitary matrices that are automorphisms of the Hilbert space. The initial state may be either a mixed state or a pure state. The set of final or accepting states is a subspace of the Hilbert space. The above is merely a sketch of a quantum Turing machine, rather than its formal definition, as it leaves vague several important details. For example, how often a measurement is performed. See for example, the difference between a measure once and a measure many QFA. This question of measurement affects the way in which writes to the output tape are defined.